Hi Nicholas. Hi Shania, you're super fast. Hi Joel, hi Bradley. Right, so quite a few of you come in. Abigail, great. Um, okay, so welcome everybody. Now what we're going to be doing today is going through a fair amount of the 2062 booklet. Have any of you started this booklet? Okay, that's great. Okay, so you should see on the screen what I've got up there for the standard. Now what we did last time was the rates of reactions. So you looked at what made a reaction go, it needed collisions of the right orientation, and you also needed sufficient energy in that collision for it to overcome the activation energy. And then you looked at how concentration, temperature, surface area, and catalyst could change the rate of reaction. Now I'm mentioning those again because we're going to be looking at those same things and how it affects another type of thing with the reaction, which is equilibria. And so if you looked at the other part of the standard that you're going to be doing is equilibrium. So we're looking at the nature of it, that it's dynamic, and I'll go over it. We're going to see the changes. So can you see temperature comes up here and temperature is over there? So temperature affects both rates and equilibrium. Concentration and concentration, so it affects both. Pressure would actually affect both, we just haven't done it there. And then addition of catalyst. So addition of a catalyst actually has no effect, but you need to know that. So Abigail, what do we mean by orientation? Molecules sort of generally have a roundish shape, but they could be quite linear, and depending on how it's connected, so let's say HCl. So HCl has a chlorine on one side and a hydrogen on the other side. Now if it collides with, say, ammonia, so NH3, what you want for that reaction to occur is that the nitrogen in ammonia grabs the hydrogen from HCl. So can you see if ammonia collides with HCl, where it collides with the chlorine in HCl, do you think the nitrogen is going to be able to grab the hydrogen? No. So what has to happen is that for the collision to be effective, when that collision happens, the hydrogen must be colliding with the nitrogen in order for it to grab it. So that's what we mean by orientation. In other words, when they collide, are the right sides of the molecules connecting, or is it the wrong sides? So does that make sense? Yep. So you can get thousands and thousands of collisions that don't necessarily lead to a reaction. It could be, the usual one is there's not enough energy to overcome the activation energy, but it could also be the orientation. Okay, if I just need two hydrogen atoms to collide to form hydrogen gas, well, obviously the orientation doesn't come into it because we've only got two atoms. Okay, and that's why actually, for other reasons as well, but when two atoms collide, it's quite a quick reaction. But it's also because of the activation energy being lower, because there's such a well, they're just so reactive atoms because they need to get a full stable energy level. Okay, right, so we need to, let's go back, sorry. We need to look at the equilibrium constant, which I hope that we're going to get to today. And then, so that's all in 2062, and then these last three bullet points are discussed in 2063. So that is all for the 2063, so we're not going to look at that now. So let's look at this one. What is a equilibrium reaction? So what they've got here is ammonium chloride. the reaction we were talking about with ammonia and HCl, it forms ammonium chloride. Now if you heat it, as he's going to be doing it here, you can see it's a white solid. But as he heats it, okay, there was first that moisture that would be there. As he heats it, what's going to happen, he's going to be giving enough energy for that material to decompose into ammonia and HCl. But as it decomposes and the two gases, ammonia and HCl, comes off, can you see what's happening up here again? The ammonia and HCl are forming ammonium chloride again. Can you see sort of what's happening there? So I've got a solid, it's decomposing. You can't actually see ammonia and hydrogen chloride gases, but you can see the effect when they've combined again up there. So can you see we've got a reaction going from ammonium chloride to the gases, and then the gases to the solid ammonium chloride again. I'm just going to take that back a bit. Okay, so that's just to show that a lot of reactions are reversible. In other words, it can go one way, and while we're making those products can combine and form the reactants again. So these different reactions have this different degree of reversibility. Some reactions aren't very reversible at all, okay? Others reverse very easily. And that's where that equilibrium constant comes in, which we were talking about later. So that's the first thing, is that reactions are reversible. It's not necessarily always one way. The next thing is, for that equilibrium to work, for it to get into a state where the products can go to reactants, reactants go to products, and backwards and forwards all the time. I don't know if you notice that what he's done over here, he's put a stopper on this test tube. So is this test tube now exposed to the atmosphere or to the rest of the classroom? No, correct. Okay, so this is what we call a closed system. The ammonium chloride is kept only in this side of this container, so it's a closed system. If I took that vapor, if I took that stopper off, do you think I would get as much ammonium chloride again? And would I keep on getting this reversible reaction between the solid to gases, gases to the solid? No, correct, because it's going to just simply disperse and fill the room, and there'll be fewer collisions. So for an equilibrium system to happen, we need a closed system. So closed just simply means it must be sealed in some way from the rest. So you could have a closed system within a room or a closed system within a test tube, but it's got to be isolated. Okay, right, so that was the first bit that you need. Here's now another thing to show what's happening. So if I just show this, you can look up these things as well. They are in OTL. Otherwise, I have given it up here for that Chem Toddler and so on. So what we're doing is, there's orange dichromate. So dichromate is orange, whereas chromate is yellow. So if he's adding base, the base is reacting with this NH, so with the H plus, and can you see it's gone yellow? Now he's going to add acid, and what do you think is going to happen before he does it? So can you see it's gone orange? So he's formed dichromate again, which is this one. Now he's adding base, and you can see he's forming this one again. And we can go backwards and forwards forever, adding these different things. So this is again to show that reactions are reversible. That's the point of this, and I'm just going to pause it there. Right? So it's first of all to show that reactions are reversible. Secondly is we can push a reaction from one side to the other by using a variety of different means. So here is, we need H plus to make this reaction go to the right. So if I add more H plus, so if I'm adding more over here, do you think I'm going to get more collisions between this side, or am I going to get more collisions between that side if I'm adding H plus? Okay, we're going to get more collisions on the left-hand side. Correct, Abigail. So if I've added over here, I'll get more collisions, and so we're going to be forming the orange dichromate. But when I add base, as is doing at the moment, then I'm removing some H plus. So where am I going to get more collisions now? Collisions between the dichromate and the fewer H plus ions, or collisions between the dichromate and the water? So see Abigail's typing. It'll be now, well, no, actually now I've forgotten what my question is. I'm going to get more, if I remove the H plus by adding base, then I've got fewer H plus, so I'm going to get fewer collisions here, and there'll be more collisions on this side. So sorry Abigail, you may have been correct depending on my question, but I've forgotten how I framed it. So I'm going to get more collisions on this side. If I'm going to get more collisions on this side, can you see the reaction is going to proceed to the left, and it's going to turn yellow? Do you follow that reasoning? Yeah. So it's all to do with the number of collisions and which ways it goes. So if I added more dichromate to the solution, then it's going to be orange first because I've added more dichromate, and dichromate is orange, but then there'll be more collisions and it'll shift to the left. If I added more chromium, that's yellow, then I'm going to have more collisions on this side, so it's going to go to the right and become orange again. So that is how we work with an equilibrium. We can shift the position from the left to the right of that equilibrium. And this is given a particular name called Le Chatelier. Now I'm just going to type it into this chat box because I haven't actually got it. As you can imagine, what is the nationality of that chemist? He was, I think, in the 1800s. Anybody do French around here? Okay, so he was a French chemist and he dealt with these systems. And so he came up with what we call the Chatelier's principle, which you will have to learn and use. And basically he said, if you've got a system at equilibrium, now I haven't actually stated very much what equilibrium meant. Equilibrium simply means when you've got the same number of collisions happening on this side to that side, and so that we'll get as many going of those particles going towards the right as those particles going to the left. So we're constantly having reactions going on, but the rate of the forward reaction is equal to the rate of the backward reaction. So for every product I'm forming, I'm going to be getting reactants. So that's an equilibrium. Now Le Chatelier said, after all his experiments, if I stress the system by changing it in some way, then the equilibrium position is going to move to relieve that stress. So as you can see, if I'm adding H plus, so if I move this on to when you added H plus, okay, now he's adding base, so it's going yellow. So I think he's going to be doing it one more time for the H plus. He's now adding H plus, so I'm just going to stop it there. If I'm adding H plus, then that's my stress. I've added H plus. So according to Le Chatelier, the equilibrium position is going to move so that to relieve that stress, in other words, I've got to remove H plus via the equilibrium movement. So which way is the reaction going to go? forward to form dichromate or backwards to form more chromate. So the stress was adding HCl, the forward one, correct, Abigail. So the stress was adding the HCl, so the way to remove it is by getting rid of it, by reacting it so it forms a dichromate in water. So when we say, if I add HCl, according to Le Chatelier, the stress is adding H+, so the equilibrium position shifts to the right in order to remove the H+. So going back to, and as you can see what's happening, it's forming the orange dichromate. So if I go back to where it was the sodium hydroxide, okay, so the stress here is I'm removing H+. So according to Le Chatelier, if I'm removing H+, the system has got to try and minimize that change. So it's got to try and make H+ to make up for the stuff I'm removing. So which way is that equilibrium position going to move? Towards the left or towards the right? Towards the left, correct. Because can you see if I'm removing this, then the reaction's got to try and make some more H+, and the only way it can make H+ if my I get a faster reaction going towards the left to make more H+. So that's the way an equilibrium system works. First of all, if something's at equilibrium, it has to be a closed system. Now, I know this is open to a beaker, to the air and so on. And yes, with time this would all evaporate, so you could have it sealed. But otherwise the reaction is happening just within the liquid. It's not actually happening within the air, and that's why we can have something in equilibrium over here. Okay, then we can change that equilibrium position in the reaction by adding something or removing something. So we're adding a stress. Now there are other ways we can add the stress. So that was the first one. If I'm adding something, can you see I'm changing the concentration? So if I'm adding H+, can you see I'm increasing the concentration of H+? Does that make sense? Yep. Okay. Now there are other ways I can stress the system. The other way is by temperature. If I change the temperature, I change, I stress the system because it's a change. Also, if I have gases, for a gaseous reaction, if I change the pressure, obviously if I change the pressure here, it's not going to have really any effect because it's all happening in a liquid. But if I had a gaseous system, it would be important. So let's have a look first of all at this one. Now this is actually a great simulation. It is also on OTL. Okay, so if you just googled MHHE, okay, you should come up with it. It also have audio with it because it actually explains it as you go. Okay, so here they have Fe3+, the reaction, okay, reacting with SCN minus, that's thiocyanate, and you can get the iron thiocyanate ion being formed, and that is the sort of brickish red color. So basically, if I'm now adding more thiocyanate, okay, so I'm adding more of this, what do you think is going to happen to the color? At the moment it's an orange because it's sort of like a cross between the thiocyanate ion complex and the colorless thiocyanate. And then we have the yellow Fe3+. So if I'm adding more thiocyanate, which way is the reaction going to go? Is it going to go darker because I'm forming more of this? Or is it going to go paler because I'm forming more of that? It's going to go darker. So if I add some of this, oh heck, I know what's happened. Sorry, this is just an image. Sorry, I'm being very idiotic. This is not the simulation, it's just the image of the simulation. I need to get over here. Sorry, I feel like a bit of an idiot here. No, that one, it's not that one. It's not that one. I'm going to actually just do that. Okay, sorry, this is the real thing. So if I, okay, I'm going to go back. So now if I'm adding this, then I've added more. Okay, so it's going to shift to the left, and can you see it's gone darker? Now, because this is a simulation where it's talking away, I can't go faster than that. But you can play around with it and listen to it, because then see what happens when you add some more of the complex. And I'm hoping it's going to, no, it's not going to change very much. Okay, so that's the change in concentration. We can also do something with a change in pressure. So if I just click on this one, or there's a back button, so I'm going to do now the other one. If I remove Fe3+, so that's another stress, so I'm changing the concentration, I'm decreasing the concentration of the Fe3+, and so hopefully that's going to go down. Okay, so initially it's going to go darker. I don't know if you saw that, and then it's gone lighter again. It first goes darker because I've got more of this, but then as the equilibrium position shifts to the right to try and make more of this, it's gone lighter. So let me try now change in pressure. Here I've got purple iodine and iodide atoms. Okay, so they have just mentioned in this explanation is at very high temperature, because you won't really get atoms floating around. So if you have this equilibrium, okay, these arrows show that the forward reaction is the same rate as the back reaction. If I increase the pressure, what do you think is going to happen? So if I increase the pressure, this plunger is going to go down. Now in my reaction, I've got one molecule on this side, and I've got two on that side. Or two, they're not molecules. So I've got one particle on this side, and I've got two on that side. So if you think of what is pressure, it's the amount of collisions on the container. So if I'm making the area smaller, there's going to be initially a lot more collisions on the sides of the container because I've made it smaller. So to minimize that, I've got to try and decrease the pressure or decrease the number of collisions on the sides of the container. And correct, Abigail, the way to decrease it is to decrease the number of particles in the system. So the way it does that, my two will combine to form one, so I'm going to be halving the number of substances, particles, so there'll be fewer collisions. So if I increase the pressure, then initially it goes dark because I've got lots of iodine now in the small system, but then can you see it, it'll actually also stay purple because I'm going to have more iodine. So it's shifting, and you can see I'm getting more iodine because it's trying to make fewer particles. Okay, so it initially went dark because it was in a smaller volume, and then it went darker because I'm making more I2. Does that make sense? So I'm getting more particles of iodine. Yeah. And right, so now we're going to do the other way. Okay, great. Is I'm going to decrease the pressure. So I'm going to make it more spacious. So by making it more spacious, there's going to be fewer collisions for the side of the container. So according to Le Chatelier, the reaction's got to move to try and relieve that stress. So I've made it fewer. So it's got to try and change it so we're going to have more collisions. Okay, so you can see that the opposite's going to happen if I increase it. Okay, so it would go paler first of all because I've spread out the iodine, and not just that, as it reacts now to try and get back to equilibrium again, then the iodine is going to break up more to form the iodine atoms, because it's got to shift to the right to try and increase the number of collisions, to make them the same again, the number of collisions against the side of the container. So that's the way pressure will affect things. So we've done concentration, now we're looking at pressure. Last one is a change in temperature. So this one is also can be done with pressure because you can see it's gaseous. Anything that's got gases can be affected by pressure. But we can also do it with a change in temperature. Now, it doesn't actually tell you whether this is exothermic or endothermic. So, and I can't remember actually what will happen, so we could work this one out. What happens if I increase the temperature? So just have a look at the color. So at the moment it's sort of a lightish brown because it's a cross between this colorless N2O4 and the dark brown NO2. So if I increase the temperature, then is it going darker? We're going to see which way it's going to happen. Okay, he's just said, okay, right. Now, he did say the reaction, what it was, but we can also work it out. If I'm adding heat and the equilibrium shifts to the right to form more brown NO2, the change is adding heat, so the system wants to remove heat. So if it goes to the right, what was that reaction? Exothermic or endothermic? Endothermic, correct. Because endothermic needs energy to work, so you've got to add energy for it to work. Exothermic gives off energy. Now, first of all, I am just checking, because this was done in the 2.4 standard. Is everybody clear what exothermic and endothermic means? You're all welcome to say no, don't feel, oh, everybody else knows. So, okay, yep, okay, great. So, endothermic, it needs energy. So, if I'm adding heat and the chemical equilibrium shifts to the right, and we see that because it's gone darker, it means that forward reaction was endothermic, because the reaction's trying to use up the added heat to try and get rid of it, and the only way it can do that is by going forwards. So if I now do the other way, I decrease the temperature. So I think you can already work out what happens. So I'm putting it around us. So what's going to happen is, remember, it's endothermic. So I've got it. One way is to think of coolness. But it's really like removing heat. Okay, so if I'm removing the heat, then the equilibrium has to be shift in the exothermic direction. So it's got to go back to try and give off heat to balance the heat we removed. Okay, so you can see it's gone paler because we've now got more nitrogen, dinitrogen tetroxide and fewer nitrogen dioxide. So that's a really good system, interactive to use, and it sort of explains everything as well. You just listen in, and it's a really good explanation. So let's go back to our slideshow. So you can look at the concentration, the pressure, and the temperature. And the catalyst is the other one, as you saw under that list for the standard. The catalyst has no effect. So changing the concentration affects both rate and equilibrium position. Changing the pressure affects both rate and equilibrium position. Changing the temperature affects both rate and equilibrium position, but changing the or adding a catalyst only affects rate. It does not affect temperature in any way. It does not affect equilibrium in any way. Okay, so here's now a reaction where we're changing the temperature. So you see it. This is again by Chem Toddler. So this is the reaction down here. So I'm just trying to find my cursor there. So you've got hydrated cobalt, okay, reacts with chloride to form the cobalt chloride. So this is pink, okay, so if you dissolve it in water, it's pink, and then he's could change his equilibrium by adding or removing, say, HCl, okay, or but what he's going to do it by changing the temperature. And again, we can work out, would this reaction be exothermic or endothermic? So he's heating it, and it's turning blue. So remember, this is pink. You can probably see my cursor, but I can't. Where is this cursor? There. It doesn't show up here. So the hydrated cobalt is pink, and the chloride complex for cobalt, the cobalt tetrachloride complex, is blue. So do you think the forward reaction is exothermic or endothermic? Who would like to have a go? Endothermic. I'm just going to try and work it out myself, sorry. So if it's turning blue, it means it's going in the forward direction, which means it's trying to remove heat, and therefore, yes, you are correct, it is endothermic, because it's going blue to remove the heat, which means that heat must have been given, or heat must be absorbed if it goes in the forward direction. Okay, so that's, so you can see a reaction, you can affect it in different ways, temperature, concentration. Could you do this one by changing the pressure? Could I affect the equilibrium position of this reaction by changing the pressure? No, because it's not gaseous, it's in solution, so it won't have any effect. Right, here's one where you can change the pressure, and because it's gaseous, and sorry I didn't put the G there, okay, and we're going to be changing the temperature over there. Now have a look. It's quite hard to spot when I change the pressure, because what happens when you push the plunger in and you're increasing the pressure, you're obviously going to be having more particles in the smaller area. So initially it's going to look darker because you've made the area smaller. Because then the equilibrium is going to try and re-establish itself. So we're going to, first of all, we've now done the opposite way that we saw before. So if we make it the area smaller, it's going to be darker, and then this equilibrium position is going to try and re-establish itself. So by increasing the pressure, by Le Chatelier, we want to decrease the pressure, and the only way we can do that is by forming more colorless N2O4. So if you have a look, it goes darker and then it gets a little bit colorless. Then he decreases the pressure, and you can see it first goes lighter and then it goes darker again. It first goes lighter because you've just got now fewer particles in that space per unit volume. So let's have a look. You've just got to look very, can you see it's getting darker? But now, can you see it's gone lighter? It was darker and then it's gone light, and now, okay, it's lighter and now it's gone darker. Do you want me to show it again? Because it's the sort of thing that you have to see a few times. Whoops. Oh dear, now I've blown its little brains out. Okay. I'm going to just go like that and make it replay. Oh dear, I dragged it and it doesn't like it. Okay. Okay, let's look at this one in the meantime. This one, we're going to be changing the temperature. So as you saw last time, so it's just got to get started again. Did you actually see that change in color with this gas one? Yep, you did. Okay, so it goes darker, but then it goes lighter because of the reverse, because of the equilibrium. So here it's equal color. It's the NO2 giving it that color, and we've got cold water in over here, and it's hot water over there. You can sort of see the steam and the condensation, and you can see the ice on that one. And then it doesn't take long when you can start seeing that this one where it's hotter is going darker, and this one is lighter. And that's again because of that endothermic, exothermic. So what's happening here is because it's colder, the reaction is going to try and release heat. Over here it's hotter, so the reaction is going to try and remove the heat. Okay, so sort of questions often ask you on things like that. They'll say, what observation would you expect and why? So would you have expected it to go darker? I mean, they would have had to tell you that it was endothermic or exothermic and which direction, or they could give you the observation and ask you to work out whether it's exothermic or endothermic. Right. Now, here is Wananta has got a few good simulations as well. So I'm going to go to that one. And sorry, I've got a whole pile over here. Okay, here's another simulation that talks about the change in temperature. You can see it's a video and you can listen to it. And then you can have some questions to work out what's exothermic or what's endothermic, and so on and so forth. So that's also quite a nice thing, and it's also on OTL if you want to work through that. All of these that I've got here should be on OTL. And there's another one about changing the volume. Right, so I wanted, yep, this one actually. So I'm going to reset. Now, if I have, say, only my iron and my thiocyanate, okay, then I'm going to react them. So if you can sort of, I'll just pull this further down. So what it's showing is that reaction, okay, iron and thiocyanate. So what we would expect in the beginning, there won't be an equilibrium set up, and these are going to react until I get an equilibrium. So let's have a look. So I keep on reacting, and can you see this is my thiocyanate coming, getting fewer and fewer, and this is my my complex iron being formed, getting more and more and more. And I can just keep on reacting it, and it doesn't change. So you could also be given graphs. I must admit I haven't really seen much yet for graphs from the exams, but there's nothing to say that an examiner can't come up with graphs. So can you see what's happening here is my concentration is decreasing because I'm getting reactions, and I'm getting more reactions between the reactants to form the products, and then nothing is changing. Can you see that? My concentration is not changing. So when the line is flat, we often say, oh, the reaction has stopped. That's what you learned at level 1. Has the reaction actually stopped? Is everything just now not doing anything? Correct. The reaction actually is not stopped. It's now reached equilibrium. So in other words, we're going to be having collisions between the iron and thiocyanate, and we're going to have the thiocyanate just breaking. It doesn't have to really collide. It could just fall apart to form the ions again. So initially we didn't have any of the iron thiocyanate complex, and then it sort of increased, and then it stopped increasing because the amount of thiocyanate breaking up equaled the amount being formed per unit time. So this is the equilibrium part. This part over here, where the concentration is changing over time, it's actually changing, is when the system is not in equilibrium. So we're having more of a forward reaction than we are having of a backward reaction. And you can play around and change these to see the effect. Then I did want to see, there was one other one, sorry, this one. So if we're looking at the number of molecules, let's reset, because what we want to come on to is the equilibrium constant. Now, the equilibrium constant is a way we measure where that equilibrium position lies. And the way it's done is we take the concentration of the products and multiply them together, and then divide them by the concentration of the reactants. So that ratio between products and reactants is going to be my equilibrium constant. So it's always the products divided by the reactants. So if my products, if K is equal to 1, what can you tell me about my concentration of products and my concentration of reactants? Are they different or are they the same? They'll be the same. So if I react my blue, those are the reactants, and it's going to be turning red. So initially I have lots of blue and I had no red, but it's reacting to form the red, and then because there aren't very many particles here, it doesn't form a nice smooth line as what we saw. But can you, this is to show that reactions happening all the time. It's and it will come back together again. Yeah, there you go. Okay, so this is the equilibrium part, and you should see that we've got approximately equal number of blues to reds, reactants to products. Not, exactly equal all the time, but overall. Now here we've only got 15 atoms, but 15 atoms, is a minuscule amount. You normally have millions and millions and millions and trillions of atoms or molecules. So that's why you'd get a much smoother line. But that's when, as I say, we have equal number of products to reactants. Now I'm going to reset it, and I will say, I'll actually put on to high the temperature, just to show the difference. If I play it now and I've changed the temperature, can you see it's dropped a lot more quickly, okay, before it's reached equilibrium? So increasing the temperature will change the rate, and so it'll make the equilibrium be reached a lot more quickly. Temperature does also affect the equilibrium constant a bit, but not very much. But you will see a small change when you do the calculations, which I want to do next lesson, not this time around. Okay, so you can see it's still around about 14, 15. It may have moved it slightly the other way, but we've still made K equal to 1. If I've made K bigger than 1, now this I think is a fault in the diagram, because if K is bigger than 1, do you expect more reactants than products? Or do you expect more products than reactants? Okay, if K is bigger than 1, you would expect more products, because remember the products are on top and you divide it by the concentration of the reactants. And this is where this simulation to me is incorrect, because we would expect it to go a lot more red. Okay, so I think they made a mistake here, and this should have been less than 1. Because if I play this over here, then can you see I do get a reaction, but I don't get very many products. So this is really, it should have been less than 1. So if K is smaller than 1, I have more reactants than products. So you can see I've got more blue reactants than the red products. So that should have been smaller than 1. Okay, so this is still my equilibrium, but it's now, you know, it's a different position to what we had before. If I make K bigger than 1, so just imagine this was now the other way, K is bigger than 1, and I play this, then we would expect a lot more red. So you can see here, it's not an equilibrium yet because it's still changing, but I'm forming more and more products, and now it's reached equilibrium over here. So just what I wanted you to think of in this lesson is, what is an equilibrium? So in other words, it's a reaction that has to happen in a closed system where you have equal rate of a forward reaction to the back reaction. So although it doesn't look as though there's a change when we just sort of look at the color stays the same or whatever, there is a reaction constantly happening at particle level with the, you know, equal rate of forward reaction to back reaction. So that's the first thing about what an equilibrium is and when it occurs. Then the other things I want you to know from this lesson is that you can draw these graphs and sort of, I'll just stop there and just wait for it to get into equilibrium again. Oh, sorry, I pressed the wrong button. I wanted it to pause it. So you can see here it's not at equilibrium yet because it's still changing, but now as the graph flattens out, it's now going to be at equilibrium. So I want you to be able to look at the graph and see when is something in equilibrium and when is it not. So the graph is always either concentration or number of particles or something like that on the y-axis, and then time on the x-axis. So we've got a few more minutes left, and I just wanted to show you what happens when we change other things. Okay, that's actually the constant. Okay, I'm just going to close that one because I didn't want that. Right, okay, so here's one where we look at the concentration, and if we change the volume, and if we change the, so if I make the volume quite small, right, we can calculate our equilibrium concentration, and as I say, that we'll do all next time, but just to show that there's my concentration of my NO2 and my N2O4. So that's at that volume. If I increase my volume, can you see what's happening to my numbers? Okay, so have a look at here. Is it getting bigger for the blue or smaller for the blue? So I hope you saw it was getting smaller. I was getting a decrease in concentration there and an increase in concentration there. Oh, hang on. Sorry, I've gone. Forget that. I said the wrong thing there. Notice your concentration is going to change. You want your mole fraction. The reason being, if I increase the volume, is my concentration going to decrease for both of them? Just generally. Okay, if I'm increasing the volume, I'm going to have more space, so it's going to be, for both of them, they'll actually decrease in concentration. But if I look at my my mole fraction, so we see how much have we got of this relative to that, then it'll explain. So sorry, you should have looked down here, it's my mistake. So the NO2, if this goes up, Now can you see the blue? I'm getting more and more blue relative to the red. So the simulation is good in that it's showing that the concentration is sort of changing for both because I'm increasing the volume, but I'm getting relatively more blue, and that's because I've got to get more particles to try and keep the number of collisions with the sides the same, to keep the pressure the same. And you can do the same thing with the temperature. Right, there was one other one I wanted to do, so not that one, okay, not that one. Okay. I was going to come back for that. No, I think, okay, let's stop there because there was a question. Oh, hang on, I think it was this one. So if we're disturbing, just to show what these graphs look like without any calculations, this equilibrium constant, we'll be looking at calculations next time, where can you see it's the products multiplied together divided by the reactants. So if I have lots of A and B, and I don't have any C and D, equilibrate means I get the reaction going to equilibrium. So you can see A and B decrease and C and D increase. What happens if I now add more A? So I'm adding more A. Did you see, this is the A line because these are the reactants. As I'm adding more A, can you see this line going up? And if I equilibrate, can you see what happens? So initially I had reactants going down, products going up. I've made a change over here, and the change is adding A. So I've got a lot more A than B now, because A and B were going down at the same rate. Now I've got a lot more A, but can you see A is going down before it gets to a straight line again, and so is B? But my pink line is going up. Why would that be? So thinking of Le Chatelier and the stresses, if I add more A, that is my stress, in which direction is that equilibrium position going to move? Is it going to move towards the right, or to form more C and D, or towards the left to form more A and B? It'll be in the forward direction. So if the stress is adding A, so the reaction's got to move to remove A. So here it goes, I've added A, so now the reaction's trying to remove A. Here B also decreases, even though I haven't added more B, but it has to decrease because my reaction is shifting to the right. So every A reacts with B to move it across. And so that's why I get more C and D. So if I had now again more A and B, okay, and I have full amounts of A and B and no C and D, and I equilibrate. What happens if I now add more C? Okay, so I've added more C, so I've added more over here. So in which way is the equilibrium going to shift? So equilibrate, can you see C and D have gone down? So C has gone down, D has gone down, but A and B have gone up. And that's because the stress was adding more C, so the equilibrium position has to shift to the left to get rid of that added C, and so I'm going to form more A and B. Okay, so you can sort of see what happens here if you wanted the figures. We'll be doing some calculations, as I say, next week. And you can play around with it, seeing what happens when you change. Let's do one more and then we can stop. So say we had A and B and no C and D, and we equilibrate. What happens if I remove something? So say I removed all of, or most of B by precipitating it out or something, okay? And now the system has to reach equilibrium again. Because the stress was removing B, the equilibrium position has to shift to try and add B to make up for the stuff I've removed. So can you see A and B went down, but now I've removed B, so B is down here, and B is in the black. So B is, as it reaches equilibrium again, it's trying to increase the amount, and because the equilibrium is moving to the left to increase B, I'm increasing A as well. And of course the pink line is going down because C and D have to collide to, and therefore get less to form more of A and B. So what I wanted to do today was just get that overall picture, see what's happening on the graph level, see what's happening on the particle level. And then next week we're going to be looking at calculations and that sort of stuff, and also acids and bases. Are there any questions before we go? Nope? Okay, well then see you next week. And as I say, you're welcome to email me any questions or anything during the week as well. Right. Bye.